Okay, so let's see some questions from the 9709 syllabus permutations and combinations topic. Let's look at some questions from 2010. So paper 6-1, June 2010. I don't remember what the question number was, but find the number of different ways that a set of 10 different mugs can be shared between Lucy and Monica if each receives an odd number of mugs. Now, odd number of mugs, and we have to share 10 different mugs. So let's see the options that we have. So we have Lucy, we have Monica. So it could be combinations, could be 1 and 9. It could be 3 and 7. It could be 5 and 5. And then the patterns will repeat. So we could have 7 and 3. We could have 9 and 1. So as you can see, these two are repeated, right? So 10 different mugs, and we need to group them together this way, right? So for these two, for the first two, we will times it by 2. 2 times by 10. Actually, let's go one by one. So this one is 10C1 times by 9C9, right? Then plus 10C3 times by 7C7. These two are multiplied by 2 plus this one 10C5 times by 5C5, and that's it. So let's calculate for them. So 10C1 times by 9C9, that is 10. 10C3, and then 7C7, 120, plus 10C5, and then 5C5, 252. So we get 2 times by 130 plus 252, 512. Okay, all right. Another set consists of 6 plastic mugs, each of a different design, and 3 china mugs, each of a different design. That means they're all unlike objects. Find in how many ways these 9 mugs can be arranged in a row if the china mugs are all separated from each other. Okay, so now this is very important and this is very interesting. So the constraint is on china mugs, not on the plastic mugs, right? So we have 1, 2, 3, 4, 5, 6 plastic mugs. 1, 2, 3, 4. Actually, these are all plastic. So if we do this, as we can see, this is 6 factorial. So because we have 6, 5, 4, 3, 2, 1, sort of like this. And 3 china mugs, that means since they are going to be separated from each other, how many places can we arrange them? 1, 2, 3, 4, 5, 6, 7. So for the first one, we have 7. And when one of them is gone, obviously that means 6 remain for the other 2, and then 5 remain for the last one. Right? So another way we could write this same information is 6 factorial times by, we have 7 choices or 7 places, and we need to arrange 3 items, 7p3. This and this are exactly the same. So 6 factorial times by 7 times by 6 times by 5, we get 151200. Another set consists of 3 identical red mugs, 4 identical blue mugs, and 7 identical yellow mugs. Okay, now we have identical items now. Okay, these 14 mugs are placed in a row. Find how many different arrangements of the colors are possible if the red mugs are kept together. Now we have how many 14? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. The red ones have to be together, right? So somewhere R, they are 1 unit over here, right? But we don't have a problem with the other ones, right? So how many units left? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 factorial. Out of 4 are blue mugs and 7 are identical yellow. Technically, we will have internal rotations of the R also, so we could do 3 factorial divided by 3 factorial also because they are still identical. So this 3 factorial can be cancelled out. So we have 12 factorial divided by 4 factorial and 7 factorial. Wait, sorry. 4 identical blue mugs, 7 identical yellow mugs, if the red mugs are kept together. We have 3, 9, 6, 0. That's it. All right, so let's look at the question from variant 6.2. So 2010 6.2. Right, okay. 9 cards, each of a different color, are to be arranged in a line. How many different arrangements of the 9 cards are possible? So all of them are different colors, so obviously 9 factorial arrangements, right? So 9 factorial arrangements, 3, 6, 2, 8, 8, 0. 9 cards include a pink card and a green card. How many different arrangements do not have the pink card next to the green card? Now, what we can do over here is we can find out the number of arrangements in which they are together and subtract it from the total number of arrangements. So, number of arrangements in which green and pink are together. So we have 9 cards, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And green and pink are together. So how much we can make? 1, 2, 3, 4, 5, 6, 7, 8. 8 units times by 2 factorial units for the green and pink interpretation. So the answer would be for the do not have not pink and green not together would be simply 9 factorial minus 8 factorial times by 2 factorial. So minus 8 factorial times by 2 factorial. So we get 28240. Okay. Consider all the possible choices of three cards. Now this is combination. Choices of three cards from 9 cards, with the 3 cards being arranged in a line. Okay, all right. How many different arrangements in the total of 3 cards are possible? Okay, so this is still arrangements. So this is, we can see this in different ways now. For the first place, we have 9 choices. For the second place, we have 8 choices. For the third one, we have 7 choices. So 9, 8, 7. Also, we can just do 9p3. Out of 9 choices, we need to arrange only 3. It's 9p3. So this is exactly the same as 9 times 8 times 7. So 9p3, that is equal to 5. 4. If you just want to make sure that this is correct, so 9 times by 8 times by 7, that is 0. So that means they're equal. How many arrangements of the 3 cards in part 3 contain the pink card? Now, when one of the cards is chosen, so this means that pink card is already there. And obviously, since this is part of the arrangements, for the pink card, obviously it could be over here, it could be over here also, it could be over here also. So 3 possible places for the pink card, right? 3 possible places for the pink card. And for the rest of the 2, I need it from the rest of the 8 cards. So 8p2. Pink is already selected, so I have to find from the other 8, or we have to take from the pool of the other 8 cards left for the rest of the 2 places. So we have 3 times by 8p2, 168. Right. How many arrangements of the 3 cards in part 3 do not have the pink card next to the green card? Okay, so over here, now we have a different scenario over here. The pink card cannot be next to the green card. Okay, so it's similar to what we did over here, but slightly differently, right? So we have the pink card, but it's not next to the pink card. So what we'll do is, we know the total possible arrangements of 3 cards, and from this we will subtract the possible arrangements where the pink and the green are together. So pink and green together in 3 cards. So we have pink, green, and some other, right? So that means 2 of them are already selected. So that means I have to select from 7p1. So 7 choices for one of the places, and 2 factorial for the, we will have 2 factorial for these 2 units, and 2 factorial for the internal rotations of p and b. And for all the possible selections for the last digit. So 7p1 times by 2 times by 2, we get 28. So pink and green not together is going to be equal to 504, because this was the total number of arrangements for 3 cards, minus, this is 28, so 504 minus 28, 476. Right, okay, now let's look at 6.3, 210, 6.3 major. Okay, 3 identical cans of cola, 2 identical cans of green tea, and 2 identical cans of orange juice. 3 cola, 2 for green tea, 2 for orange juice. So let's write over here. So 3 colas, we have 2 green teas, and 2 for orange juice. Let's call that orange. Let's call that juice, sorry. Okay, arranged in a row, calculate the number of arrangements if the first and the last cans in the row are the same type of drink. Okay, so this is important. So we just have 3 choices, and we have 3 plus 2 plus 2. That means 7 7 possible slots. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now we just have few possible options where this is cola, this is cola, this is tea, this is tea, this is juice, this is juice, right? So when the colas are at the ends, how many possible arrangements do we have? We have one more cola inside, and we have 2 teas, and we have 2 juices. So the only unlike thing over here is the cola in this block over here, right? So what we just do simply over here, how many items do we have? 1, 2, 3, sorry, 1, 2, 3, 4, 5, 6, sorry, 5. So this is 5 factorial divided by 2 factorial, 2 factorial, because of the because tea cans and the juice cans are identical. Now, when the teas are at the ends, we have 3 colas and 2 juices. So it's the same thing, but differently. 5 factorial divided by 3 factorial, 2 factorial. And for this one, again, we have 5 factorial, 3 identical colas, and 2 identical tea cans. So when we add them up, because these are the number of possibilities, 5 factorial divided by 2 factorial, 2 factorial, plus 5 factorial divided by 3 factorial, 2 factorial, plus 5 factorial, 3 factorial, 2 factorial. So 5 factorial is basically 120. So 120 divided by 4 plus 3 factorial times by 2, that is 12. So 120 divided by 12 plus 120 divided by 12. So 30 plus 10 plus 10. So that's 50. Right. Part 2. The 3 cans of cola are all next to each other, and the 2 cans of green tea are not next to each other. Okay. So part 2. Now 3 cans of cola are, so we have 7, again 7 slots, 1, 2, 3, 4, 5, 6, 7. The colas are all next to each other. 1, 2, 3 colas are next to each other. And the 2 cans of green tea are not next to each other. So this means that, okay, let's see this first. So we have 3 cans of cola all together, 2 juices, right? But the 2 cans of juices, sorry, 2 cans of tea, they can be placed here, they can be placed over here, they can be placed over here. One of them, each one by one, they can be placed over here. So we have 4 possible choices for tea, but since we just have 2, right? So we can arrange it that, right? So how many items do we have? 1, 2, 3, 3 factorial first times by, since we have 4 times by 3 for 2 cans, or 4p2 also, we could also do that, 4p2 also, right? And divided by, simply divided by 2 factorial for the identical juices and 2 factorial for the 2 identical teas. So we get just big 2 factorial and 2 factorial will cancel out with the 4, so it's just 3 factorial times by 3. So 6 times by 3, which is 18. So this is it. Hopefully in the next video we'll cover the October 2010 questions also. Bye bye.